So today we're going to learn where we need to use all these exponent rules that we've been talking about. And we're really going to answer the essential question, why is it helpful to write numbers in different ways? Today we're going to learn about scientific notation. We're going to be able to write and compare numbers in scientific notation. So I'm going to start you off right now with a question. What is the mass of the Earth? So mass is not weight, it's how much matter, how much stuff there is in an object. So I'm going to write this. Here is the mass of the Earth. Now, a kilogram is kind of like a small bag of onions, for lack of a better word. And this is how many kilograms there are. It's 5 septillion, 974 sextillion, 200 quintillion. Help! Who wants to write that? Who wants to type that over and over again? The chance of making a mistake are great trying to figure out what that number is. So we need a way to write really big numbers like this and really small numbers more easily. And that is what is scientific notation. Now on page 52 in your book, they describe scientific notation. And I'm going to draw your eye right here where I'm circling. There is an example of a number in scientific notation. Scientific notation has 3 parts. The first part is a number, and that number always is greater than or equal to 1 and strictly less than 10. An easy way to think of it is there can only be 1 digit in front of the decimal point. Then there's going to be the multiplication sign, and I already described that they've brought the x back in, and then it's a power of 10. So if the number is greater than or equal to 1, basically I say if you've got a really big number, that will lead to a positive power of 10. And if you have a really small number, it's going to lead to a negative power of 10. Here comes our discussion with those negative exponents. So big number, a lot of money is a positive thing. And a really small number between 0 and 1 is going to have a negative exponent. And let's walk through some so you can see that. So here's an example of a number written in scientific notation, and we want to see that in what's called standard form, the numbers we're used to. The first thing we're going to do is we're going to write that 534, and we're not going to put the decimal. So you'll see my cursor kind of holding the decimal spot. We're going to look at the exponent, and since the exponent is bigger, is a positive number, we need to move it so that the number gets bigger. So it's sitting between the 5 and the 3, and we're going to move it 4 places to make the number get bigger since that 4 is positive. So we're not going to go around the 5 in that direction because it'll get smaller. We're going to go around the 3, and as we move around the 3, that would be 1 place. Around the 4 would be 2, and then we ran out of room on the 534, so we had to add 2 zeros. So the decimal started between the 5 and the 3, but it moved 1, 2, 3, 4 places because of that positive 4. So 53,400 is the same value as 5.34 times 10 to the 4th. So we're going to do this letter A on page 52 together, and then I'll have you do the letter C. We're going to skip over B for a second, okay? So we're going to take and write that number that is in front of the scientific notation, and we're not going to write the decimal. We're just going to put our cursor or our pencil and hold that spot. I'm then going to look at my exponent. Notice it's positive, so I need to move the decimal to make this number bigger because of the positive exponent, and I need to move it 5 places. So I'm going to start by moving it around the 4. So it went from 7.42 to 74.2. See how it's getting bigger? So we're going to move it around the 4 and around the 2. We've moved 2 places, but we needed to go 5. So we're going to have to add zeros, 3 zeros to get it to those 5 places. So go back between the 7 and the 4. Around the 4 is 1, around the 2 is 2, around the 0, 3, another 0, 4, another 0, 5. 742,000 is the same value as 7.42 times 10 to the 5th. I would like you to try this one, so pause the video, please. And when you're set, come back. Let's see how you did. So on this one, I'm going to put my cursor between the 3 and the 7, and I'm going to move it 2 places to make it bigger. So around the 7 and around the 1, and I have 371.4. The number one mistake, guys, is to just add zeros, the number of zeros. But it's not that. It's you have to move the decimal to represent multiplying by a power of 10. Okay, so now let's talk about what if there's a negative exponent. Now the process is basically the same. You're going to write that 327 and you're going to put your cursor where it was, but don't write a decimal point. When I see the -3, the number is going to get smaller. So I'm going to move it in this direction. So around the 3 would be one place. Now I have to add a 0, that would be 2, add another 0, and the decimal would be 0.00327. This lead 0, the calculator often gives you, and some people write it, it can be there or not be there, and you are good. Okay, let's try one of these. I'm going to let you pause the video and see if you can do this one yourself, and we'll come back and do it together. Okay, so here I'm going to write that 6.1, but not put the decimal and just put my pencil in between the 6 and the 1. Because it's negative, I need to make it smaller. So I'm going to go in this direction. And I'm going to go 2 places. So I'm going to go around the 6. So I've used up one of those 2, and then I have to add a 0. So it went from in between the 6 and the 1, 1, 2. Now again, this lead 0 can be there or not. Final answer, 0.061 is the same value as 6.1 times 10 to the -2. Okay, so now we're going to go in the other direction. How do you take a standard number and write it in scientific notation? So the first thing I look for in the number is all the non-zero digits. So do you see 3725? I'm going to write them, and I'm going to put the decimal strategically with only one place in front. That's proper scientific notation. I'm not going to make it 37.25 or 372.5. I'm going to put it in between the 3 and the 7 for proper scientific notation. I kind of come right down here. The way the book does it, I'm going to do it more like this. Then I'm going to write the multiplication sign, and then I'm going to write a 10 in the base. The next thing I need to do is figure out how many places did I move the decimal. Now, first of all, this is a really big number, so my exponent is going to be positive. The next thing I'm going to do is I'm going to look at how many places I moved it. And in this number, the decimal is sitting at the end. 3,725,000, and the decimal is at the end. So we are going to wrap around the 0. That's 1, 2, 3. Around the 5 would be 4. Around the 2 would be 5. Around the 7 would be 6. And I got it where I needed to be. So it would be 3.725 times 10 to the 6. So in this number, first of all, right now, I'm going to guide you through it. You're going to write all the non-zero digits down. The next thing you're going to do is put the decimal in the right spot with only one digit in front. You're going to write the X for multiplication, and you're going to write 10. And now you have to figure out the exponent. See if you can do this one yourself. After that little bit of guidance, pause and give it a go. Okay, so we would have written 1.414. And now how many places did I move it? 1, 2, 3, 4, 5, 6, 7. And it would be positive because this is a really big number. Now, what if it's a really small number? We're still going to write the non-zero numbers, which would be the 316, and we're going to put the decimal with only one digit in front, not 31, not 0.316, but we're going to put the decimal whether it makes it 3.16. Now we're going to ask ourselves, how many places did we move it to get it there? Around a 0, around a 0, around a 0, that's 3, and one more would have put it where we want it. This time, however, that 4 is going to be negative because this is a really small number. So let's take a look at this one. I want you to think right now, where would the decimal go? What would our numbers be in front? And what would the power of 10 be? Pause the video and see how you do. So I would have put the decimal in between the 8 and the 7. So the start would look like this. Then I'd put the times, and then I'd put 10. And now I have to write the power of 10. The decimal started here, but it's going to end in between the 8.7. So we moved it around a 0, 1, around a 0, 2, around the 8, 3. So the decimal is going to be 3, but now is it positive or negative? Because it's a really small number, it would be negative. Please pause the video and do F and come back when you're set. Only has to move one place this time, right? So in between the two ones, moves it one place, and again, it's a negative because it's a really small number. So where this is useful, one of the first things, is that it's really, really easy to order numbers that are in scientific notation. Don't put them in standard form and try to figure out who's the biggest and who's the least. If you have them in proper scientific notation, which these all are, look at the numbers in front. This doesn't say like 18.3 or something like that. They're all in proper scientific notation. In our next video, we'll talk about what if they aren't. And then you're going to use your power. So in this case, it's referring to the table at right. Order the countries according to the amount of money visitors spent in the United States from greatest to least. So we look to see if they're in proper notation, scientific notation. And then what you're going to do is you're going to look at the power of the 10. And since we're looking for the greatest, it would be the 7. One of these two countries spent the most money. Now, if you have those equaling, this is called the magnitude, but if those power of 10s are equal, you now look to the numbers in front and ask yourself, which one is bigger, 1.06 or 1.03? And since 1.06 is bigger, the United Kingdom is first in line. Canada would be second. Now we're going to go to the power of 6, and we have to come out to the number in front. Mexico has a bigger number in front than India, so Mexico would be next and then India. So you make sure they're in proper scientific notation. You use the powers to determine the greatest, and be careful, sometimes they'll ask for least to greatest. If the exponent is the same, you use the number in front to determine it. And when you write your answer, you write it in the kind of the original forms, or in this case, you would write United Kingdom, Canada, Mexico, India, like answer the question. Don't just write little numbers over here like this is first and this is second. Write an answer, and it's kind of in blue right here. So this is your chance to order these. So the first thing, are they in proper scientific notation? They are. We'll talk more about that in the next video. Now look at your powers of 10. And in the end, I want the names of these cities in order from least to greatest. This is the U.S. cities that were visited by overseas travelers. And we want to know least to greatest this time, so be careful. Pause the video and come back with a list of the 4 cities in order from least to greatest. Okay, so let's see how you did. It should have been Boston, the Metro DC, Las Vegas, and then Los Angeles. So if we look here, we're looking for the smallest this time. They're all in proper scientific notation. So it was, it looks initially tied between Boston and DC, but then you come to the number in front, and this time we're looking for the smallest. So that's why Boston went first and DC went second. Now when we go to the power of 6, we're again looking for the least this time. Las Vegas is smaller than Los Angeles. So the final thing we're going to do today is just talk about, when do we use certain units? So imagine if you could walk at a rate 2 meters per second. It would take you 1.92 times 10 to the 8 seconds to walk to the moon. Is it more appropriate to report that time in the number of seconds or in the number of years? So 1.92 times 10 to the 8 seconds is the same value as 6.09 years. They are the same amount of time, but one case you're reporting in years, In one case, you're reporting in seconds. So basically what we talk about here is if the distance or if the object is really big, you want to use a bigger unit to describe it. This doesn't really show very clearly that length of time, but boy, 6.09 years does. Again, I want to remind you, if we convert seconds to years, these are the same value. But the minute I see that, I'm like, holy cow, it'll take me 6 years to walk to the moon. So if you have a really big distance, a really big object, you want to use the bigger unit. In this case, years is bigger than seconds. So the measure of 6.09 years is more appropriate. The number 1.92 times 10 to the 8 seconds is very large. So choosing a larger unit is more meaningful. You want a bigger unit for a bigger distance or object. You want a smaller unit for something that is smaller. So I'm going to ask you to see how you do on this one. In an ocean, the sea floor moves 475 kilometers. Kilometers means 1,000 meters. A meter is like a yard, and a kilometer is more like a mile. Okay, so a kilometer. So 475 kilometers over 65 million years. Is it more appropriate to report this rate as 7.31 times 10 to the negative fifth kilometer per year, or 7.31 centimeters per year? So should we be talking about the movement as part of a mile or part of a centimeter? Is the sea floor moving a lot every year, or is it moving a really little even each year? And then pick the appropriate unit. Pause the video and just see if you can make a decision between those two, and then come back. So if we look at these two, kilometer is like part of a mile, and centimeter is like part of an inch. It's like inches. The ocean floor moved 470 kilometers, but it did it over 65 million years. The ocean floor is like not moving a lot every year. It's moving a very little. So in this case, the smaller unit would make sense because it's moving a small amount each year. So we would use the 7.31 centimeters per year. The number is very small, so choosing a smaller unit of measure is more meaningful. The smaller the thing you're measuring, the smaller the distance, the smaller amount of time, you should be talking about a smaller unit. And if it's bigger, like walking to the moon, you should be using a bigger unit. So I just want to end. We started with talking about the mass of the Earth. I just want to end with talking about another place that scientific notation is used. And I'm going to welcome you to a term which is called the mole. It also has another name called Avogadro's number. Avogadro means it's the guy who discovered it. If I had discovered it, it would have been called Woodruff's number. It's just somebody's name. And there's kind of a nickname for it called the mole. And it's not the little animal that like makes tunnels in your yard. It's kind of a term like the term dozen. If I talk to you about a dozen of something, you immediately know what the number is, and you know that that number is 12. So the word dozen is the same as 12. Well, the mole is the same as this number. Holy cow, right? This number is known as Avogadro's number or the mole, and we never write it this way in science. We write it in scientific notation. So 6.02 times 10 to the 23rd is a mole. It's like 12 is a dozen. And you might say, why would we ever need that? Because we're going to talk about maybe the number of hydrogen atoms or molecules. And when you're talking about the number of molecules or molecules or atoms in something, it's a lot. So they talk about mole, and this is used in chemistry. Where else in science do we see really big or small numbers? You think of anything else? Another place I think of right away, again, is astronomy, which a lot of you have been doing in science right now. So when you're talking about the distances between planets, it's really big numbers. We want to talk about those in scientific notation. So today we learned a new way to write numbers so that we can sort of see and compare them easier, especially in science. So remember that really big numbers in scientific notation will have a positive exponent, and really small numbers, like between 0 and 1, like 0.000078, will have a negative exponent. Scientific notation will always have a number in front, and the decimal will be placed so there's only one digit in front, so that this number is greater than or equal to 1 and strictly less than 10. We use that darn X for multiplication, thank you, scientists, and then a power of 10. So guys, I hope you have a great day. That's scientific notation in a nutshell.